Okay, hello everyone. We will do combinatorial game, which sounds fancy, but okay, it's something quite simple. In most of these problems, you just have two people, like two or more people, usually two. We'll call them Alice and Bob because why not? Alice and Bob are nice. And they'll be playing some sort of game. And because this is math, they'll do like weird stuff. Like if the number is n, you replace it with n by 2 or 2n. Weird stuff like that, which only math people do. So it's not like an actual game. In case you came like that, it was like clickbait. So one of the most basic things, or like common ideas that comes up in combinatorial games is just copying the other person. So like, see what I mean? Let's just do an example. The problem is this. You have a table and then there is a large supply of coins of the same size. So there are two players, Alice and Bob. Alice goes first. So a player puts a coin somewhere on the table, and then the next player, they alternate turns, also places a coin on the table. And they keep repeating this until there's no space left on the board to place another coin. And if you cannot place a coin, you lose. So the question is to find who has the winning strategy. So for example, if the coin was like very big or something, yes, like this. So then like after one player plays, it's already over. But if it's a bit smaller, you could imagine a situation like this, where after like the second move, there are no moves left. So
Wait, the person who plays it first can win. There's a strategy.
what is the strategy?
Like the first person can like take the center of this whole rectangle. The first person can put this coin on the center of this rectangle.
Okay. And
And then if the second person puts like some coin on some place on board, then the first person can just do it in half symmetry opposite to that.
yeah,
Like the symmetry going from the center of the
exactly.
yes.
So this look also we're assuming the coin is small enough, so like at least one coin will fail. So the strategy is that the first player plays in the exact center, the geometric center of the rectangle. And every time the second player places a coin anywhere, you just reflect that coin across the center and place a coin there. So, Dole, if you see why this works. The idea is that the first player always has a move. So every time the second player plays, suppose this is the place in here. Suppose you could not play here. Then like your path is being obstructed by some other coin. But then when that coin had been played, you must have played at the corresponding thing here. So this coin could not have been placed either. So that is a contradiction. So this strategy actually works. And yeah, the idea here is just that I can always move and therefore I can't lose. And so I must win. Does that make sense to everyone?
Yes.
Does that make sense to everyone where everyone includes the 14 people apart from Anurag? And
Yeah.
I just joined. Can
Yes.
you give me a summary of what happened?
yeah, so like I was just discussing one of the most important things in combo games, that's being able to copy the other person. And like just an example where there's a huge table, a rectangular table, and you have an infinite supply of coins. Two players, Alice and Bob, take turns placing coins on the table. You can't overlap over another coin. And then whoever is unable to place another coin on the board loses. And the Question is to find who has a winning strategy. And the solution is that the first player plays in the center, and every time the second player plays somewhere, he reflects that position across the center and plays over here. This way he can always ensure that he has a move, so he never loses. And so he must.
I
That's
see.
all. Okay, nice. So that's just, we could have done a lot more examples of this, but the questions I know of them are just too hard to do to start off with. So let's just do some other stuff. Let's introduce more notation because we are math people and introducing notation is what we do best. So in a game, let's suppose there are like finitely many possible configurations in the game. For example, this kind of stuff that I'm going to introduce would not be valid for this game because there are an infinite number of ways of how these coins can be arranged on the table. So we are not going to bother with that. Instead, we'll look for like finite deterministic games where there are like finitely many possible configurations. By that, I mean, suppose you have this game where there are, say, I don't know, 3 piles. One has 3 stones, one has 5 stones, one has 15 stones. And each time you take some number of stones from some pile, and whoever takes the last stone wins. So in this game, each configuration can be represented as ABC, where A is the number of things in the first pile, B is the number of things in the second pile, C is the number of things in the third pile. And as the game passes, there's like only finitely many configurations that can happen because there are only 4 choices for the first thing, 6 for this, 16 for this. So this way, like we can actually like label every configuration. Does that make sense?
Yes.
Okay, so in such a game, do you all agree that at every position, either the first player playing from that position or the second player must have a winning strategy? Right, like if not, the game has to end eventually. We're also assuming that the game is final. So eventually one of the people from every possible position must win. So based on that, we're going to classify any configuration as one of the two. We'll either call it a P position or we'll call it an N position. So if it's a P position, it means the player who just played wins. And we'll call it an N position if the next player who is going to play wins. So I'll just take a simple example of this. Suppose you just have, let's take a simple thing. Okay, let's actually begin with this. This is probably famous, but let's do this. There are 2 players, Alice and Bob. On your turn, you can say like up to 3 new numbers. And it has to be like in ascending order. So like suppose Alice says 1, 2. Bob can say 3, or Bob can say 3, 4, or 3, 4, 5. And whoever says 21 loses. Suppose Alice starts first, who has a winning strategy? Okay, I'm curious, how many people do not know this game? Interesting. Okay, like this is just 21 deaths with 2 people, which is just scam because there is just a direct way to win. And let's actually look for this direct way, because there are actually people who do not know this yet. And you can generalize to like make this 3 and 21 to any numbers. So let's think of it this way. 21, is it a P or N position? Recall that P means the player who just played one, and N means the player who's going to play just wins.
It's in P position.
No, it's actually an N
N.
position, because if you said 21, that means you lost. So the player who just played actually just lost. So this is an N position. What about 20?
It's in P position.
Yes, because the player who just played is going to win, because you're forced to say 21. What about 19? Yeah.
It's N.
Are you sure? You can say up to 3 numbers.
Yes, so the next person will say like 20 and then you will have to say 21.
Yes, sure. Sorry. This is an N position, because the player who is going to play next says 19 and 20, and the player loses after this. What about 18? It's the same thing. You say
Also
18,
N.
19, 20, and it's an N position. Okay, but what about 17?
17 is in P position.
Yes, because from 17, you can say like 17 or 17, 18, 17, 18, 19, and you will lead to an N position, whatever you do. So therefore, it must be a P position that you're at. So what about 16? Let's just do until some numbers.
N. We can reach the latest P position, right? Like 17 in the next.
Yes, exactly. So 16 and 15 become N positions, because from 15 and 16, you can go till 17, which is a P position, which you want to reach. Basically, if you're playing to reach a P position, it means that you have a winning strategy. Does that make sense?
Yes.
And from 14, you can only go to N positions. So this is P. Are you? No. Wait, all this is wrong. It should be mod 4, not 3. Shouldn't 17 be N? 17, 18. Of course. You're right. 17 means that 17 has already been set. So you have to start from 18. Sorry for the stupid error. Right. So if 17 has already been said, this is this, this is this. And if 19 has been said, you can say 20 and 12. Right. So 17 is an N position. And from 16, you can either go to 17, 18, or 19, which are all N positions. So it is a P position. Because the guy who's going to play now, whatever he does, he's going to reach an N position, and so he's going to lose. So do you see a pattern? If something is a P position, what does it mean for the few numbers before it?
Then it is P.
Like if this is a P position, what does it mean for the numbers before it?
Like the next person can just get to that number and
Yes.
he will win. So N.
Yes. So if a number is P, yes, the 3 numbers before this are all N. And after that, it becomes.
After that, it will be P because that will reach N.
Yes. So Do you see that which numbers end up being P here?
0 mod 4x.
Yes. If 4 divides a number, then K is a P position. And 4 does not divide 1. So 1 is an N position. And so which player has a winning strategy?
The second one.
Yes, so the second person. And from this, you can also see that the winning strategy is to always say a multiple of 4. So if the first player said 1, then you say 2, 3, 4. If the first player had said 1, 2, you say 3, 4. And you always end at a P position, which is a multiple of 4. Right, so okay, nice. So let's try the more general version. You can say up to N numbers in a row. And whoever says M loses. So we can repeat the exact same. We know that M is a P position. No, it's an N position.
M minus 1 is.
Yes, M minus 1 is a P position. And if you have a P position, what can you say about the numbers before it?
The N numbers before it will be all N.
Yes. So M minus 2, M minus 3, all the way till M minus N plus 1. All of these are going to be N positions. So what does this mean? Like which things can you say are N positions and P position?
Like GCD of M minus 1 and M minus N plus 2.
No, GC, like what are you looking mod? Like this is periodic mod which number?
It is mod N plus 1.
N plus 1, yes. So mod N plus 1. So if a number K is congruent to M minus 1 mod N plus 1, it's a P position. All right, so someone asked what N and P positions are. I'll just go back to this. Yeah. So a P position, if the player who has just played to reach that position has a winning strategy from that point, and it's an N position, and like P stands for player and N stands for next player. So in N position, next player, the one who is just going to make a move, has a winning strategy. Does that make sense? Nice. So right, we repeated the same thing here, and we had that if K is congruent to M minus 1 mod N plus 1, then it's a P position. And if K is not congruent to M minus 1 mod this, then it's an N position. So the number we're starting off with is 1. Oh, I mean, we're starting off with 0 in a way. Because like the initial situation is 0 and you're starting from 1. This also means that we messed up some definitions in the previous thing. Because 4 does divide 0. Never mind. It's fine. Yes. So 4 does divide 0. So 0 is a P position. And the N player, the next player in this case, is the first player. So if it's a P position, it means the second player has a winning strategy. It's everything else is the exact same, just I messed up some definition. Right. So this means that the game itself, when it starts, is a P position if n minus 1 and plus 1 divides n minus 1, because you want k to be 0. And it's an n position otherwise. And what does a P position mean? Like which player has winning strategy? Based on the definition of P and N.
But if n plus 1 divides n minus 1, then it would be n position, right?
No, we said that if k is congruent to m minus 1 mod n plus 1, then it's a P position and it's an n position otherwise.
Okay.
So a P position means that the player who just played, which is the second player, because the game hasn't started yet, and because it's the first player's turn, like symbolically, you can just assume that the second player just played. So this means the second player wins. And if not, an n position means that the next player who's going to play is the winner. So the first player. Does everyone understand? Or if I'm going too fast, like do tell me, I'll slow down, do things more recently.
It's fine.
Okay. Since no one else said, I'll assume there's no problem. Okay, let's do this problem. It's more interesting, I think. Find all pairs m comma n such that the second player, or let's not even phrase it this way. So you have an m times n grid. In this case, m is 4 and n is 6. So initially there is a token in the bottom left corner. So on a player's move, they can only move this token up and right. And the aim is to be the one to reach this top right corner. Basically, if you can't move, you lose. So for all each pair m comma n, decide that who has a winning strategy. That is the problem.
Wait, we can only move one move to the upper right.
You don't have to move all the way. You can move here. You can move it here, here, all the way up,
Right.
and so on.
So you can move any number of moves in a row.
Yes,
or
you can move
column.
any number of squares up or to the right. Can you repeat the question? Yeah. So you have an m by n grid, m rows and n columns, in this case 4 by 6. You have this yellow token in the bottom left corner. So Alice and Bob take turns at moving. And on your move, you can move the token any number of squares up or any number of squares to the right. So for example, this, moving it here, or to any of these squares are all valid moves. But if you're on this square, you can only move here and here. Does that make sense? And the aim of the game is to reach the top right corner.
Okay.
The person who reaches the top right wins, yes. Okay, let's actually do this in the same way as we've been doing for the previous problem. If you reach the top right, you win. So
Wait,
what position?
can I just try?
Yeah.
Can I just express my idea? So like there are m plus n minus n diagonals in it.
N plus n minus n?
Like we can consider 6, 3 and 5, 4 are just like P position. The player who gets on it wins, right?
Yes.
And then
No.
why?
That means this is an n position, not P.
So the next player who plays it, oh, so the one
Yeah,
who
if the
reaches that
token is on this
wins.
square, the next player will win.
Okay. Then the squares before it, those 3 squares before it, will be
Yes,
P
all of
position.
these. So the top right corner, if you reach there, you win. So this is a P position.
Yes.
And this is an N position because from here, the next player can just directly move to the top right. Does that make sense?
Wait, were you annotating something?
Oh, is my screen not visible or something?
It wasn't working for a time. Can you just present again?
It is fine for me.
Like you can see the top right, I mean the top row and the rightmost column.
Yes,
filled.
yes. I can see the label. Right?
Yeah, that's right.
Okay.
So
For
next, let's
every
look at right.
for
Go on.
every P position, all squares below it and on the left of it will be n, right?
Yes. So if there is a P position here, this means everything here and here is going to be N,
Yes.
because from that you can reach. So the question is just to
Yeah.
find these P position. So what is this square?
This square is
That's
clearly a P position.
Yes, this is a P position because you can only reach N positions from it. And from what we discussed, everything below it and to the left is all N. What is this square?
It is a P position again.
P again.
Yes. And this?
It is a P.
Yes. So, and this just holds for a general M by N grid. Nothing special about 4 and 6. Yes, as the first player wins if and no, the second player wins if and only if M is equal to N. Oh, that's a not equal to. Yeah. If M not equal to N, then the first player. So the bottom left square, is it a P or N?
It is P if M is equal to N. It is N if M is not equal to N.
Exactly. So the set of all P positions is just this diagonal from the top.
Yes.
So if M is equal to N, this means second player wins. And if M is not equal to N, this means first player wins. Does that make sense?
Yes.
Yes.
Yeah. And instead of phrasing it as P and N positions, do you see a way to phrase this as an explicit strategy?
What did you say?
Like this P and N position thing works, but can you just phrase it as an explicit strategy? Like instead of saying fill the boards with P and N.
One square, I think. Move
Yes,
one
as
square.
Arjun said. No, moving one square is not the thing. The idea is to stick
Okay.
to the diagonal. So if M is not equal to N, on your first turn, you just make the move that moves to this diagonal. The next player will have to move away from this diagonal
And you just
And you
keep
just
moving
move.
to the
Ah,
diagonal.
yeah.
Yes.
Okay, yeah.
And then when they move away, you. And because your final desired thing is on a diagonal, you can reach it.
For this case, it is the first player wins.
For this case, it is.
The first player wins in this case, 4 and 6.
Yes, the first player wins by moving to this. Yes. And in other cases, the second player wins. Also, just a second, Miro is being updated apparently. I'll just refresh. Okay, right, what next? Yes,
Can we a bit
exactly.
formally say that if the first person sticks to the diagonal joining m comma and m minus 1 comma n minus 1, so it should win? Like, does it work?
Yeah, the strategy of the first player, if m is not n, is to go to move to this
Yeah.
any square in the diagonal. Yeah. And if m equal to n, it's the same strategy, but the first player doesn't have it because he's forced to move away from the diagonal. Is it some revolutionary update? I doubt. It's just a random update that keeps happening. Okay, so in all of these problems so far, we've been finding an explicit strategy in most cases. Like the PN thing works, but most of these cases we've just done an explicit strategy. So sometimes you don't need an explicit strategy. You can sometimes just like say, assume the other person wins and then prove that you could somehow have used that strategy to your advantage. So how many of you know chess? Like just the rules of chess. You don't need anything. Not chess, chess, the game. CHESS. Okay. I see quite a few. Okay, so there exists this problem. Double chess is the same as chess, except each move you can make like two moves. So white makes two moves, black makes two moves, and it goes on. Prove that with optimal play, white will not lose.
But can you just represent the problem statement?
Represents a problem statement.
I
Like I'll
can't
just
get
open
it.
a Lichess board if you want.
Okay. It will be
Yes,
nice.
yes, please.
You would get to learn chess.
Is it fine if white draws?
Huh?
Is
It's
it
fine
fine
if
if
white
white
draws,
draws?
yes. Wait, how tools? Yeah, okay, so we are not actually allowed to make two moves in a row, but just to see a chessboard. The source of the previous problem is Lithuania 2010.
And what's the
And that
position?
I'm in grade 1.
No, I
Uh,
mean 2010 in the
I'm
LTST. So
I'm
whatever.
asking like that grid problem was from Lithuania.
Great problem was from what? Could you repeat?
Was the problem source that is cited right now?
Yes, the find all m comma and such that and the diagonal thing.
Okay.
You can go to goal. Okay. Yes, makes sense. This way we can make random moves without the engine killing us. So I'll just repeat the problem.
What if, okay,
No, it's fine. Go on.
what if white does nothing? as in take the knight ahead and bring it back or something like that.
Exactly, that is the solution.
Oh,
Like,
okay.
like suppose with optimal play, white still was going to lose. So this means that whatever white does, black has some strategy that they will employ to defeat us. But then white plays starts with knight f3, knight g1, and now uses whatever strategy black has, and white wins, which is a contradiction.
Bruh.
What?
Yes.
Can you repeat?
So suppose that black had a winning strategy, like
Okay.
purely winning, no draw.
Okay.
Then white plays knight f3 and knight g1. And now it's the same thing, but with like white and black swap, because it's now black swap. So now white will use whatever strategy black planned on using. And then white will not lose this. So white can always ensure white wins or draws.
No, but after bringing the knight back, isn't it black's turn?
Yeah,
Then
it's
how?
black. So like black
Okay,
is now
okay.
in the role of white because black is now starting in a way.
Ah, okay. Yeah, nice.
So it's just the roles got swapped. So yeah,
It is a slick proof.
example that exists. It's like scam and all, but yeah. Right. Okay, let's do a less scam version of this problem. So let m be a integer greater than n square. N is also some positive integer. So initially there is a board and the number m is written on it. So on your turn, from the current written number on the board, you can subtract a multiple of n or you can subtract a number less than n. So essentially, like you can subtract any number of the form 1 till n, then 2n, 3n, 4n, and so on. And the aim of the game is to like reach 0.
Are there
Yes,
two players playing?
yes, there are 2 players, Alice and Bo. Also, Pranav Shriram is good. It's not my fault that I end up taking nice problems from there. Yes, so there is a number written on the board which is bigger than n squared. So on your turn, you can either subtract a multiple of n or you can subtract a number smaller than n. And the aim of the game is to reach 0. So for example, suppose n was 2. N is 2 is a terrible small example. Suppose n is 3 and we begin with the number 11 on the board. Then you're allowed to subtract anything of like 1, 2, 3, 6, 9. So like if the first player subtracts 9, then we replace this number 11 with 2. And then the player 2 just subtracts 2 and makes it 0 and the player 2 wins. So like, does everyone understand how the game works?
We can't go negative, right?
You can't go negative.
Wait, can't you subtract 1?
You can, sure. Oh, also, not even proof for the winning strategy. Prove that first player wins also.
I think I have a good scammy proof, but I don't know if it would work or not.
I don't think the scam is that go on.
Like consider second pair wins, then like
Consider.
consider for the sake of contradiction, consider the second pair wins.
Okay.
Then like second player can take any number and just subtract that m and get any number k.
But the first player starts. Yeah.
Yes. So first player just subtracts any number.
Any number?
Means any number from 1 to n or 2n, 3n, 4n till n squared.
Okay.
Or then we get a number k, and then the second player subtracts another number such that k is greater than some m squared. It can just subtract from like 1 to
Also, like the rules are specific to n. You can't replace n with any other number because these set of numbers you're allowed to subtract is like very dependent on n. So you can't really induct on n that.
so like the person who reaches 0 wins or the next person wins.
The person who reaches 0 wins.
Clearly the second person can win.
The second person does not win. Like prove the first player wins. And the problem is not wrong.
Wait, then
Oh. I did not know that.
What did you not know?
Like what? Oh, it's direct message. Krishna said the solution, which he did a couple of days ago. Oh. Okay, that makes sense. Okay, we'll do this 2 ways then. So, can we do it by the P and N way? Yes, that's what Krishna did. Yes, starting from. Okay, that's just sad then, because then the scam approach is not that fun. But the scam approach is pretty good. Still shows scam approach. Okay. So I'll just do the scam approach quickly, I guess, and then we can do the nice way with the P and N position method. So the scam approach is this. Suppose the second player instead had a winning strategy, right? So the first player replaces m with m minus n first. And then use a different colors. So suppose the first player replaced m with m minus km. Okay. If the second player's strategy is to also subtract a multiple of n, as in if he replaces it with m minus kn minus jn, then this is stupid because on the first turn, A could have directly subtracted m minus k plus j times n. Right?
which is a contradiction, right?
No, this is not it. Like, I'm just saying that the second player can't subtract a multiple of n. So they do subtract some number r from 1 to n minus 1. So this is the clever part. So for m minus n, you're replacing it with m minus n minus say r1. For m minus 2n, suppose you're replacing with m minus 2n minus some r2. And so on until at least m minus n square. So m minus n square minus rn. Right? And because m is greater than n square, we know that there are at least these many terms. So we have n such values, and they're all between 1 to n minus 1. So this means that there is some I and j such that Ri is equal to Rj. Do you all agree?
Yes.
And without loss of generality, assume I is less than j. So the first player begins with m minus I. Let's suppose this is equal to R. Then B replaces this with m minus in minus R. And now from this, A subtracts j minus I times n, which converts it to m minus jn minus R, which was supposed to be a winning position for the second player. Which is, I mean, this is supposed to be a winning position. So you can do this.
Yes. But
Yeah,
for
it's-
that, the
Yes.
Alice has to know about Arun and Aaron.
You need to know about what?
Like it is correct, but it is a bit slow.
Yes, I am not saying this is easy. The problem is mainly here because it is like, yeah, the by I'll repeat. So because the second player has a winning strategy for any move A makes. So like A could have subtracted n, 2n, and so on until n square, right? So for each of those things, B has to have some response of how much he'll subtract. So we're calling those responses R1, R2 until R. So note that the response cannot be a multiple of n, because suppose I subtracted m, made it m minus in, and B strategy to subtract a multiple of n, say jn. So now the new number is m minus I plus j into n, which the first player could have reached on his first turn directly. So this can't be winning for the second player because it's winning for the first player too, right?
But the first player might not reach it always, right?
Oh, the point is when the first player made it m minus in, the second player made it subtracted another jn, making it this number.
Yeah.
So this means that this thing is a p position.
Yes.
But then A could have directly subtracted I plus j times n on his first move. And it's a p position, so he should have won, which contradicts the fact that A does not have a winning strategy.
No, but like if the first person is subtracting minus n and the second person is doing minus n square, how will the first person do n plus 1 into n?
Like if you're able to subtract a minus n square, this already means that m is at least n square plus n.
Yeah.
So you can subtract that much.
What?
It's like A can subtract n plus 1 times n. There's a multiple of n.
But
Oh,
you can only choose up to n square, right?
no. Any multiple of n,
Okay.
this
My
goes
bad.
on like till n square and beyond.
Okay.
Yeah, I should have been clear about that. Right, so any response that player B has to be a number between 1 and n minus 1. So you have like for each value for n to n and up to n square, you have n responses, R1 till Rn. But because you only have like 1 till n minus 1, by pigeonhole, some two of these must be the same. Suppose Ri is equal to Rj equal to R. And without loss of generality, assume I is less than j. So then A will do the following thing to win. A will make it m minus in. According to B's strategy, he makes it m minus in minus R. Now from this, A subtracts this number, j minus I times n, which makes it into m minus jn minus R, which was supposed to be a p position, because if you had subtracted, made it m minus jn, the second player would have made it m minus jn minus r. So this must be a p position. So because the first player reached a p position, he wins, which is a contradiction.
Okay.
Yeah, also, let's just do the nice, normal, standard approach too, because this is not obvious at all. So let's just do the classic p and then p positions. So 0 is a what position?
0 is in P position.
Yes, because then the player who just played has won. Make sure it actually works. Yes, I think it does work. So all the numbers from 1 till n, what are they?
They are P position. N
They're what?
position, sir.
Yes, they're n positions because you can go to 0 from this.
Yes, you can just subtract.
Yeah, what is n plus 1?
It is in P position.
Yes. What are n plus 2 all the way until 2n plus 1?
It is in P position.
It's a what? It's an n
Oh,
position.
no,
them are
N
P.
position.
because you can
The,
get to it.
the person just
Okay.
can go to N plus 1.
Yes,
Yes.
because you can reach n plus 1 from these. This is an n position.
Yes.
And so this way, this means 2 times n plus 1 is a p position. So this way, you can repeat this until you show that the p positions are exactly 0, n plus 1, twice n plus 1, thrice n plus 1, and so on until n minus 1 times n plus 1. And beyond this, everything, at least n square, is an n position. These are all the p positions. You can just like do this inductively. Like,
We can get to N squared minus 1 easily.
yes, so essentially, the biggest p position is n square minus 1. So for any number at least n square, the first player, like any number at least n square is an n position. So the first player wins. Does that make sense?
It is a more natural and a nice approach.
Yeah, this is more natural. It also explicitly shows that the only case the second player wins is if you begin with a multiple of n plus 1. That is at most n square minus 1. But yeah, the first one is like has aesthetic value because it's like, this was Russia 2011.
It was expected.
Yes, like no, I'm assuming intended solutions actually be multiples of n plus 1. Russians, I wouldn't put it past them. Okay, so what next? Yes, let's do this. So obviously another important thing that goes without saying, but all these kinds of combinatorial games, many times it's just very useful to test small cases. Because sometimes it might not be easy to guess the answer or something, because you can just randomly come up with like your strategy should be to play such that the number of piles left is a multiple of 31. And like maybe that works. But like to be able to come up with such a thing, usually it's very helpful to try small cases. Like let's just do an example where looking at small cases is very helpful. And once you figure out the answer, the rest is straightforward. Just a second. My Discord is just stuck. Okay, we'll just spend a few minutes waiting for my Discord refresh. There we go. No, it finally loaded and then the refresh hit it. Yes. Yeah, this is the problem. So I'll also like do the small cases here, but like I'll just give you a couple of minutes, try small cases and see if you can guess the answer. Doing lots of small cases is actually helpful. I'll be back in a couple of minutes. Also, to clarify once again, you can just only see the mirror, right?
What?
You can only see
Yes.
the mirror. Okay.
Yes.
Wait, so the player chooses end, right? Or is it fixed beforehand?
No, it's arbitrary.
No, like, is it
Yeah, the
okay?
player can choose it. Number
Fine.
n is arbitrary in every move.
Yeah, fine.
Hello, I'm back. Kritati was saying something.
No, I was just asking if n, like, does the player choose n or is it decided beforehand?
No, the player chooses end. Every move, it changes. Yeah, also like in general, doing PN like necessarily works because of just how it is. But the point is it's not a well-defined thing and you'll need to figure out some sort of pattern. Yes, very creative names at models. Okay, I guess it's possible some of you already like are doing the problem with these names, so I won't confuse and change it.
Wait, so the only way he cannot make a move is if both are 1, right?
1-1 or 1-0.
Alright.
How would 1-0 work? Wait, yes, it does. Okay.
Okay, I'll just start doing a bunch of small cases here.
Can you
So
try 3 and 2, please?
yeah, we'll get to it. So first, I'm okay. Also, just assume A is at least B. Other thing is symmetric. So 1, 1 B wins or America wins. So M 1, 2. Oh, we should do 0 also. So 0, 0. Okay, right. So I've done the cases when a plus b is at most 6. So like, what sort of pattern do you see?
Like Marika wins if A is equal to B or A plus 1. A and B are consecutive.
Yes, that is in fact it. But also another way to see it would have been to like just see that when the numbers are like far apart, if it's like say 6, 0, 5, 1 and stuff, Ivica always seems to be winning. So you can guess that the difference of the numbers is actually something that matters. And yeah, the answer is as you said, if the numbers are either same or consecutive, then the second player wins, Marika. So yeah, we can just write that as if mod a minus b is at most 1, then Marika. And once you spot this, the problem itself is not hard. Because suppose we want to prove that this is the answer. So we'll need to do two things. First, if a minus b differ by at least 2, you need to show that you can convert it into something which has a minus b at most 1. And you'll also need to show that if a minus b is at most 1, then any move you make will cause a minus b to become at least 2. Let's just do this side. I guess it's easier. So suppose we have a and b, and a minus b is at most 1. So what happens when you use this operation? Like what happens to the numbers of the piles?
One of them increases and the other decreases.
By how much?
The difference changes by
By
at least 2.
Yes. So one of them falls by n, by 2n, and one of them goes up by n. So the difference between them, because it was 1 already, like the worst case would have been if this was a plus 1 and a, and you reduce this by 2n and this increased by n, right? So how much does this make it? Yeah, this makes the difference into at least 2, because the bigger number reduces by at least 2, and this n is at least 1, right? So now it becomes like a minus 1 and a plus 1 at least. So these numbers can't be consecutive or the same anymore. Does that make sense?
yes.
Right. So we proved that if a and b differ by at most 1, then any move you do, you'll have to make them differ by at least something. So next, the thing we want to show is that if a and b differ by at least 2, you can do this operation and make them differ by at most 1. So let's just assume without loss of generality that a is greater than b, and that a is equal to say b plus k. So the piles you have are of size b plus k and p, where k is at least 2.
You can take something near half K.
Near half k. Like, okay, so if we do half k, this ends up going to around b, and this ends up going to around b plus k by 2, which made the difference a bit big, which is not what we want. Instead, how much do you want to reduce it by approximately?
We want to reduce it by at least 1.
No, not like that. Suppose you're by like some multiple of k, not like multiple, something dependent on k. Around how much do you want to reduce it by?
K by
K,
3, like n equals k by 3.
yes. You want to reduce, like you want n equal to k by 3 so that like k by 3 might not be an integer, but then this becomes around b plus k by 3, because you subtracted 2k by 3. And this also becomes around b plus k by 3. So this is our hope, that we just hope that some floor of k by 3 or something will work. And indeed, suppose k was equal to say 3z plus, if it is just a multiple of 3, then you just take n equal to z. And very good. But instead, suppose k is 3z plus 1. So b plus 3z plus 1 and b. In this case, again, you just take n equal to z. So this becomes what b plus z plus 1. And this is b plus z. So we're happy again. They differ by at most 1. And the last case is if you have b plus 3z plus 2 and p. In this case, we'll take n equal to what? This is 2. Looks like another 0. If you take n equal to z, then this becomes b plus z plus 2 and b plus z. So
Z plus 1.
yes, we'll take n equal to z plus 1. So this becomes b plus z minus 1. Or what? Oh, this becomes b plus z, and this becomes b plus z plus 1. And once again, they differ by most. Doesn't the first player have the leverage to decide values? No. So like k, I'm just defining to be the difference between the piles. And I'm just showing that if k is at least 2, then we can do this. Also, the reason k equal to like 0 and 1 fails is because then the value of n that we're using is 0, which is not allowed. We need the fact that z is at least 1 and z is at least 0. Okay. So I guess that's it for this problem. He can choose an arbitrary. N changes every move, and the player whose turn it is, they get to choose the value of n. It's not like one player, the first player always gets to choose this n. Yeah, so if the piles are b plus k and b, I'm saying that like the player whose turn it is can choose a suitable value of n such that the piles now differ by at most 1. Does that make sense? Were you asking something? So after the first step, yeah, no, so you want to ensure that mod a minus b is at most 1. So depending on the initial position. So if the initial position already has a minus b at most 1, then the first player will be forced to make the difference at least 2. And then the second player can get it back to at most 1. Second player makes it at most 2. And since the game ends with like 1, 1, 1, 0 and stuff, which are at most 1, the second player will win in these cases. But if the difference to start off with was at least 2, then vice versa. The first player can get it to at most 1, and hence the first player will win. The problem asked when Marika, the second player, has a winning strategy. So the answer is all a minus b, which differ by at most 1. Does everyone understand?
Yes.
Okay, nice. So there was a very nice problem that I wanted to do, but I wanted a dramatic end. So let's actually do something that's famous in a way and also pretty cool. And also ridiculous, like you will not believe why this is the solution. So this is NIM. You have many piles, some finite number of piles. Each contains some number of coins. or tokens, whatever. So two players A and B, they alternate turns. So on one player's turn, he takes some number of stones from some pile, but from at most one pile. So you can't pick a stone from here as well as here. You can pick from one thing. So the aim of the game is to pick the last stone. And the problem of them asks like, across all these configurations, how do you decide who has the winning strategy? Based on just the piles, number of piles, and how many are there in each pile. So let's just do a few simple cases.
Wait,
like
can you
this-
repeat how that thing works?
Yeah, so let's suppose this is the case. 4, 1, 2. These are 3 piles. So on his first turn, you can choose to remove any number of tokens, but from the same pile. So A can remove like say 2 tokens from this pile, or he could have just removed 1 token from this pile, or he can remove like 3 from here. Anything of the sort is fine. So it's actually quite. And what's the winning state? Whoever takes the last stone wins. Let's just do a couple of simple cases, and then I'll just present the solution because there's no point in me trying to motivate the actual solution. So for one pile, who wins?
The first player.
Yes. Just A wins because he just takes the entire pile. By last stone that's remaining. For example, if this was the case, first player suppose takes off all these 3 stones, then the second player can remove these 2 stones, and these are like the last stone. Oh, last stone or stones, in case that was the confusion. You can remove multiple stones in the last move too. So for 2 piles, it's a bit slightly more interesting.
I guess A wins again.
Always. Oh, let's try this simple case.
Like make 4 and 5.
Why 4 and 5? 1
Okay.
and 1. Who
Okay.
wins?
B.
Yes, because A has to pick the stone, B will pick the other stone.
Yep.
1 and 2 who wins.
A can take the first stone. So B
Yes.
has to take, we have forced B to come to the stage where A was in 1-1 stage. So A will win here.
Yes. 1, 3.
You can again just take 2 stones.
Yeah, A will just take these 2 stones and win. Okay. 2, 2.
I take one and then the other person.
Yes. If you take both stones, second player just takes both stones and wins. If
In
you
any
take,
way, the second player wins. In any way.
yes, it's obvious for 2, I guess, but okay. 4 and 4.
Like take the first 2.
First few. How many is a few?
Like first 2.
First 2.
2. Then say, then you can move any move you want to for B. Okay. So now I will just remove 1 stone. Oh
And
yes,
you lose.
B wins. Yes.
Yes, so for this 2 pile thing, it's what we did at the first, just copying the other person. if both piles have an equal number, then how many ever you pick from this, second player will just pick those many. So
It
whenever
works
this
in
pile gets,
symmetry. Yes.
yes, so whenever one pile gets over, the other does too. And what if there is extra? Then the first player just removes stones so that it becomes equal, and then uses that strategy. Now, a funny consequence of this fact is, do you remember the Lithuania problem we did? Find all pairs m comma n such that that thing is true.
Yes.
Yes, it's the exact same problem.
What?
Don't turn things so fast, please.
So suppose the token is at this point, then it's like a distance of 1 from the top row, and it's a distance of 1, 2, 3, 4 from here, right? So you can imagine this being equivalent to like two piles, one with 1 stone, one with 4 stones. And when you move, what are you doing? You're reducing one of these numbers to anything. So if you reduced this to 0, it means that you're removing this stone. However much you're moving to the right, you can imagine cutting from this pile.
It can't be just then try to imagine it in an n-dimensional space and it works.
I guess, yes, but like this problem we did, we had the advantage that it was simple in 2 dimensions.
Like in any case, it will be the diagonal that is having the p position.
No. In more dimensions, it's not this easy at all. Like, for example, according to what you're saying that
Like taking from the topmost point where we have to reach and from the point we are starting.
so you're saying the second player wins only if they're all equal.
Yes.
Suppose you have piles with 2, 4, and 6. Second player wins.
Yes. Yeah, good.
Wait, why is this obvious?
Like you take anything from any of the 3 piles.
Okay.
We can just the first player will try to remove the first pile. Then the second player clearly wins because it is an inequality.
Yes, I mean, you don't need to remove the first pile. You can remove like 2 stones from here and all. And it's like not obvious. In 3 piles itself, it's not at all obvious, I think.
Yes, it's not.
Okay, so the real solution set is this. Suppose our piles are say P1, P2 until Pn. This Pi denotes the number of stones in the pile numbered I. So suppose, okay, just give me some random numbers. 5, 8, 11, 3. Okay. Let's actually make it a bit 18. So now we do the most random part. We will write these numbers in binary. Yes, of course, this is natural. So now we will compute. Yeah, you're actually quite close. You take the bitwise XOR. And the, yeah. Okay, so the bitwise XOR is defined this way. So we'll draw columns to just separate these digits. And we are going to do this. If there are an odd number of things, odd number of ones, then we put 1. If there are an even number of ones, we put 0. That is the bitwise XOR. 1, 1, 1.
You can just addition mod 2, right?
Yes, but okay. I thought this was easier to like explain. Addition mod 2 is more intuitive. Yes. So yeah, the answer is that this, let's call this final thing as n. It's called the nim sum. So second player wins if n is 0 and first player other. It's like obviously I did not come up
How
with
will you prove this?
Oh, proving it is actually surprisingly easy. Proving it is not the difficult part. actually.
Getting it is the most difficult one.
Yeah, I don't know how you come up with this. I will write in binary and take bitwise XOR. Bye. So like, let's just focus on
First you
proving this.
took binary and then you took bitwise XOR. Like
What?
even after getting binary, I find no motivation in doing bitwise XOR.
Yeah. Also, I will say looking at binary stuff is actually relevant in something. And in the problems that I'll give, at least one problem will involve this. Oh no, spoiler. But that problem is hard, so it's fine. So right. So like the previous problem, what does this mean? This means that if n is 0, we need to prove that any move that we make makes it non-zero. And we also want to show that if n is non-zero, we can make a move to make it 0. Does everyone agree with that?
Yes, just like the old problem.
Yeah.
Previous problem.
So let's do the first direction because it's easier, I think. So like if n is 0, we want to show that any move makes it non-zero. So suppose you're operating on this pile. Also, the symbol for XOR is like this. But okay, I'll try not to use it because it looks a bit too much fanciness. Although I think it's easier put that. But fine, that's not the point. Suppose this is the, I'll actually add, what is this? What is this number? Can any of you help? 23. Okay, so in this case, if you compute the bitwise XOR, it turns out to be 0. Where we have used the property that, and like you can see why this is true, I guess. Because if you add the same thing twice in every place, and the digit occurs an even number of times. So it has to add to 0. So yeah, I'm just telling you that this is 0. The point is to see that how changing anything makes it non-zero. So suppose we fix some row, some pile, suppose this thing, and we're making a change to it. So the sum of all of these numbers here is say some s. And this value over here is say initially x, which is 23. Right? So we initially have that s plus x is 0. Wait, hold. And suppose that after making this move also, this is still 0. So it's suppose it's y after you make the move. And we have this. Can this happen? Like, you don't need to know any properties of this function in advance. Like, just think that suppose you have some random binary number and there is some x such that this becomes 0. Also, another way to think of this function is on each digit, you just like add it and look at it model. It's the same thing as checking whether it is an even number or an odd number. And now I'm telling you that 1 0 0 1 0 1 1. There is some number y such that this also becomes 0.
Clearly x is equal to y.
Yes, because this is also like kind of reversible. If you want this sum to be a 0 over here, this has to be a 1. This has to be 1. This has to be 0, 1, 0, 0, 1. So this in fact implies that x is equal to y. Or in other words, you basically remove no stones from the pile. The pile is still as big as it was before. So that's not a legal move. So indeed, if the sum is 0, any move you make makes it non-zero. You've successfully forgotten the problem statement. Okay. So like suppose you have n piles of stones.
Oh no, I know it was just supposed to be.
Okay. Yeah. Like just a second to like take this in. Essentially, the idea is you're changing one value. So this sum, which was so nicely 0, because you changed the value, the sum has to have changed because at least some bit you would have changed. So that bit will get flipped in the final nim sum. Does that make sense? Okay, so I'll repeat. You have some stuff, whatever. So the pile that you're changing, suppose it's some number, and suppose you're like reducing this pile. So say you have to change at least one bit because this new number of stones in the pile has to be different from how many it was initially. So there must be some 0 that became a 1 or some 1 that became a 0. Suppose this 1 became a 0, for example. Then if this initial sum contained an odd number of 1s, now it contains an even number of 1s. So this value here, oh, it must have contained an even number of 1s to start off with because this was 0 here. And because now it has 1 less, it now becomes 1. And so this nim sum is not 0 anymore. So if it's 0, any move makes it non-zero. Does that make sense?
Yeah.
Okay. Nice. The other direction also isn't too hard. So I'll just do that itself here.
So if it's 0, just you can, if it's 0, you can just add 1.
Yeah, the idea is that if it's 0, then anything you do makes n non-zero.
Okay.
So now we want to show that if n is non-zero, we can make it 0.
We can do it by taking the largest ever stone piles and just then giving 1s and 0s to all the places needed.
Exactly, yes. So consider the largest pile. Not the largest pile,
Like the
Consider
largest
the
number of
leftmost
digits
digit.
in binary representation.
No, that's like equivalent. So consider the leftmost digit where there are an odd number of ones. Because if there are an even number of ones, you don't really want to subtract from there, right? Because that is nicely zero. You don't want to make that 1 into a 0 and mess things up. So there is this nim sum that exists. And it's something like this. Right? This is just random. And we have our piles P1, P2, and so on until Pk. And let's just do it. So consider the leftmost digit of the nim sum that is not 0. In this case, it's this digit, right? And because we assumed n is non-zero, there is such a digit. So because this is 1, this means there are an odd number of ones in this sum. So there is at least 1 somewhere here. Without loss of generality, I'm just assuming that P1 contains this 1. I can do this, right? By just rearranging the order of piles. That doesn't really matter.
Yes.
So the idea is that everything to the left of this is 0. I'm not going to touch this. So if I make this 1 into a 0, then whatever ones and zeros I'm changing this pile to, this number is going to be strictly smaller than how much P1 was. Does everyone agree? Because this 2 to the k here is worth, let me put it this way. This number, this is 8, is bigger than 111, right? This is 7. In binary, of course. So like any changes I make, the worst case, the largest that this entire thing becomes is like when it's all 111. But that is also like 0, 1, 1, 1, 1. But the point is that because there's this 1 here, this is bigger than that. So I am removing something from the pile. And I'm not ending up adding something to the pile. Does that make sense? Like essentially P1 is initially 1 and some stuff. I'm going to make it 0.
Can
and
you just repeat this again?
yeah. So
Unfortunately, my laptop.
okay. So P1 is like 1 followed by some stuff. I'm saying that if I make this 1 into a 0 and make this right part whatever I want, this top thing is still greater than the bottom thing.
Yes.
Because like the smallest this top thing could have been is when this is all zeros here. And the biggest this bottom thing can be when it's all 1.
Even it's all 1, it is not greater than that.
Yes. So
So
the
we can
point
just
is,
keep adding.
whatever, once I make this thing, this 1 into a 0 over here, I can make these digits whatever I want on the right hand side. Because all those, like whatever new number I'm getting, it's a valid number that is smaller than P1, right? Because I have
Yes.
something from the pile, right? So because I made this 1 into a 0, what does this become?
This has become 0.
Yes. And now in each of these things, I'm going to just choose whether to be a 0 or a 1 such that this bottom number becomes a 0.
You can do it easily because at max it can be all 1 and still the sum of them would be not greater than the number we remove.
Yeah. And the point is that this is the 0 or 1 at the bottom. It's just saying that it's an even number of ones. So depending on the parity of the number of ones over here, you decide whether to make this a 0 or 1. So you can make it some number such that this entire sum becomes 0. And so like from a non-zero nim sum, we managed to make it a 0 nim sum. And the final ending state when there are like all stones are gone is when they're all 0. So the nim sum in that case is all zeros. So because whichever player can ensure the 0 nim sum wins. So if it was 0 to start off with, then the second player wins. And if it was non-zero to start off with, you can make it 0 and the first player wins. And that is exactly the winning strategy mentioned here. Are there any questions about this thing?
Can you just tell the source of this nim sum? I would really like to read about it.
Oh, it's just nim, like the game. You can just Google it. There's a enormous Wikipedia page dedicated to this. Like I'll in fact just open it. Where is this strategy? Yeah, the Wikipedia solution is the same. It's just written more fancy.
Yes, they did it.
Yeah, but it's essentially the same. It's just a lot more random notation.
But sometimes this fanciness just makes one seem it is hard.
Yeah, that is true. But it's also like a lot less hand wavy. Like my solution was like a quite wordy and stuff. This is just like concise. It's yes, this is definitely hard, no doubt.
But
It's
this
a-
fanciness makes it a more.
No, I was talking about NIM itself. This solution to who wins in NIM. That is like definitely not easy at all. Okay, I guess like if there are no questions, then we'll actually just end the class here. I've gone beyond time, so
Like